On June 26, 2020, at 12 a.m. GMT, a CoSpace Rescue Challenge map was issued to iCooL participants from around the world. All participants were given 24 hours to develop AI strategies to solve the same challenge. In CoSpace Rescue Challenge, teams are required to build a real robot, develop and program appropriate algorithms and strategies for both real and virtual autonomous robots to navigate through both real and virtual worlds. Additionally, they have to search and collect objects while competing with another team's robot that is also searching and collecting objects in the same real and virtual worlds. During the challenge, the robot needs to overcome barriers, avoid traps, and swamps. If the robot successfully makes a deposit, the points of the objects deposited will be doubled. For University and U19 category, the CoSpace server will send the robot its own coordinates while the robot is searching in the virtual world. The location information can be used for the development of AI algorithms and strategy such as path planning and search algorithms. Additionally, for University and U19 categories, there are signal block zones which are surrounded by pink dotted lines. When a robot enters the signal block zone, its coordinates information will be blocked. The winner of the challenge will be the robot with the highest points.
Hello, my name is Hanson. I'm from Australia and I'm participating in the CoSpace Rescue U19. I've been involved with robotics since 3 years ago, and for our strategy we mark out object zones for our cart to navigate around, and the cart navigates to certain zones by using the coordinates. For obstacle avoidance, our cart avoids obstacles by converting the map into a grid, which converts clusters of pixels into numbers. That could mean that there's an obstacle or if there's a trap or swampland. And we use the A-star algorithm to navigate with this information. How the A-star algorithm works is we give the program the location of obstacles, and the A-star algorithm could calculate the shortest route between 2 points. And it does so by looking at the position around it first. So first of all, in this map I drew, the orange point would be the starting point, and the blue point would be the end point. By looking at the 8 adjacent blocks, which are highlighted in green, we can calculate their distance from the starting block. And the numbers on top of these blocks are the distance between this block and the starting block. Then we calculate their distance to the end point. As you can see, I highlighted these blocks with a gradient. The more yellow it is, the closer it is to the endpoint, and the further it is, the more red it is. Then we can add the distance to the starting point and to the distance to the endpoint together to create the total distance. This way we can calculate the shortest route to the endpoint. The algorithm then chooses the one that has the smallest sum of distance to the endpoint and the starting point, which is highlighted in green. And the algorithm repeats itself but uses the chosen block as a new starting point. As you can see, the 8 blocks around this green block are now calculated, and the total distance from the starting point and the end point are now written on top of these blocks. Then the algorithm chooses the next block and calculates the total distance for those blocks, and the algorithm stops when it reaches the endpoint. This green path would be the path that the algorithm has calculated, which would be the shortest path between the start and end point. And that is pretty much the whole algorithm. Not covering enough area inside object zones were an obstacle that we had to get through. And why that happened is that we don't have a specific algorithm that covers the object zone. So, for example, when a cart has ran out of the object zones, we will turn the cart around so that it goes back inside the object zone. And as you can imagine, that could lead to a lot of area not being covered, especially if the area of the object zone is very large. And how we fixed it is that we would spawn in random points within the object zone, and the cart would be able to navigate to it. Once it arrives at the point, another random point would be generated, and the cart would go to that point, and that would repeat. This way, the cart would navigate to almost every corner of the object zone. And finally, the largest problem with our old programs that utilizes the DJ Stella algorithm was that it could not navigate around walls, simply because we did not give the coordinates of obstacles to the cart, and the cart would get stuck. And for example, this cart would be stuck on one side of the wall, trying to navigate to the other side while not knowing that there's an obstacle that is blocking it from going through it. And how we fixed it is that we used the A-star algorithm and gave the algorithm the coordinates of obstacles so that it could generate the shortest path, while also taking the location of obstacles into its account. Thank you.
And off we go! In this demo game, we will minimize any manual intervention. Blue robot is depositing. Super object can only be picked up by the robot that generated it. Blue robot has picked up a Super Plus object, that is 180 points. Blue robot travels out of the boundary. System resets it back to the field and freezes it for 10 seconds. Red robot has picked up a Super Plus object. That is 180 points. Red Robot has picked up a Super Plus object. That is 180 points. Blue Robot has picked up a Super Plus object, that is 180 points. Blue Robot has picked up a Super Plus object, that is 180 points. Red Robot travels out of the boundary. System resets it back to the field and freezes it for 10 seconds. Red Robot travels out of the boundary. System resets it back to the field and freezes it for 10 seconds. Red Robot has picked up a Super Plus object. That is 180 points. Blue Robot wins this challenge. Congratulations!